This is the sort of double-slit interference pattern that you should have seen in association with the home experiments in Unit 5. It's essentially produced by the interference between two beams. In this program, we're going to produce two-beam interference in rather a different way. We're going to use a device called the Michelson interferometer. This instrument has been of tremendous use in many branches of science and technology now for nearly 100 years. The central feature of it is this so-called beam splitter, which takes an input wave and divides the wavefront into two halves, one of which goes up that way, hits the mirror and comes down. The other half of which goes that way, hits that mirror, comes back down and is recombined. Now, a central feature of its operation is that one of the mirrors is movable. It doesn't matter which one. In this particular case, we've chosen the top one, which can be moved up and down. That means that the path lengths covered by each of the two halves of the wavefront take different distances. They're different. Now, if the difference is such that when they come down here, the difference is a whole number of wavelengths, then we get constructive interference. If, on the other hand, the difference is such that the paths are differing by a whole number of wavelengths plus half a wavelength, then we get destructive interference. Alan.
This is the basic Michelson setup. It's the sort of setup that you'd find in many a physics laboratory, indeed in many an undergraduate optics course. The interferometer itself is down at this end, but let's just start off with our light source, which in this case is a mercury lamp. The output from the mercury lamp passes through a condenser lens so that it illuminates a pinhole, and the pinhole is placed at a focal length away from this lens, so that what comes through this lens is a parallel beam of light which continues on down until it meets the interferometer. It then meets our half-silvered mirror. Half of the light continues down this way and back and out. The other half comes in and down and out. In constructing a Michelson, an awful lot of thought must go into the moving mirror. It must move nice and smoothly. It must move smoothly over distances of the order of a wavelength of light. It would never do for it to jerk and jitter all over the place. In our equipment, it's this beam which impinges on the movable mirror, which can be adjusted back and forth. And this is done by means of a system of levers coupled to a micrometer screw. The other 50% of the incoming light, which doesn't get reflected, of course, passes straight on down here, where it meets a fixed mirror, and is reflected back, and so on, at the instrument. Well, now, there's one other little feature I should just point out, and that's the presence of this glass plate here. It's called a compensator plate, and it's there to ensure that the light which follows this path and the light which follows that path both pass through an equal thickness of glass. The output, of course, from the interferometer, both of these beams meet up in this direction here. So to see what's happening over here, I'm going to put in a lens, and in its back focal plane, I'm going to put a piece of ground glass, and we look at what happens on the ground glass. I'll advance the moving mirror in the same direction all the time, and we see our spot going bright, dark, bright, dark, bright. We're witnessing constructive interference, destructive interference, constructive interference, destructive, constructive and destructive.
So we've seen the sort of output that we get using a mercury source as the input. But what we want to do is to establish what sort of output we get in a whole variety of cases. For a whole variety of inputs, what sort of output do we get? The output, well, it's called an interferogram. Then later on in the program, we're going to see how we can work back from the interferogram and tell something about the nature of the source. Well, what is it about the source that's relevant to this problem? Well, the sort of thing that's relevant is the spectrum of the source. Now, by a spectrum, we simply mean a plot of the intensity at various temporal frequencies. To show you what I mean, let's just select 3 of those frequencies. There they are, 3 of them. To each of those, there corresponds a cosinusoid in the wave train. There we've just shown the 3 cosinusoids, 1 to each of those 3 frequencies. Of course, there's a whole string more which corresponds to the frequencies that we haven't selected. Now, even just 3 frequencies is a rather complicated sort of spectrum to deal with. So I'm going to select just one of them. That one there. And the spectrum corresponding to that is very simple. It consists of a single line, that single frequency there. That's the first input we're going to try into the Michelson interferometer. What sort of interferogram does that give rise to?
Well, if we're going to get any quantitative information out, rather than just relying on subjective impressions, we're going to have to refine the setup somewhat. And that's where this particular piece of setup comes in. Here's our Michelson over here, and it's illuminated by this laser beam. The output from the Michelson goes not to a piece of ground glass, but to a solid-state detector. Now, in fact, there's one other refinement with this piece of equipment, and that is the way that the mirror is driven back and forth. Instead of it being driven by hand, we've coupled an electric motor to it. And of course, as always, as the position of the mirror moves, so the output from the detector will change. In fact, we've fed the output from the detector to a chart recorder. The deflection along here of the pen records the intensity reaching the detector. The movement this way records the separation between the 2 mirrors. Well, let's just run the experiment and see what trace we get with our laser source. Switching on the paper. Well, the output seems somewhat cosinusoidal curve of constant amplitude. In fact, there are a few jitters, but they're probably due to cameras moving around the studio. In fact, ignoring the jitters, the amplitude remains constant, and in fact, to get any significant real change in amplitude, you'd have to run about 1,000 meters of paper.
So this is the sort of interferogram that we get from a single frequency spectrum. Now, there's a note of caution to sound here. That interferogram is a cosinusoid. But of course, it's not the wave train. It's a plot of the output against path difference. Well, now we want to broaden out to spectra that are other than single frequency spectra. Let's consider a spectrum like this, in which there is a whole band of frequencies. What sort of interferogram does that give rise to?
This time, we're using not a laser, but a rather different source. It's a white light source. There's a collimating lens there, usual, but what's really important is this filter here. That's a narrow bandpass filter. It only lets through wavelengths within about 100 angstroms. So let's just run the interferogram and see what we get.
Well, this is the sort of interferogram that we get when our source, instead of being a single line, emits over a narrow band of frequencies. Well, let's see what happens when we carry this process even further and make the band broader like this. There you can see that the breadth of that spectrum is rather wider than it was before. Well, how is it that we get that sort of spectrum?
Well, the modification which I'm going to make this time is to take out the 100 angstrom bandpass filter. So now our Michelson has incident on it all the wavelengths coming out of our white light source. Well, let's see what trace that gives us.
So we now have 3 interferograms corresponding to 3 spectra. Now, first of all, I want to start off by looking at something associated with the interferograms. Notice that there's a characteristic distance, delta LC, over which the fringes vanish. It's small here, larger here, and it's actually off the board there. Now, in terms of the apparatus, this means that there's a characteristic path difference over which the 2 beams, when they come together, give rise to 0 visibility fringes. Now, you know from the unit that this is called a coherence length associated with the radiation. And this is associated with the coherence time. It's defined by the formula that the coherence time is equal to the coherence length divided by the velocity of light. So what we have is a coherence time associated with these 3 things, and correspondingly we have 3 spectra, and associated with these spectra we have a bandwidth, a spectral bandwidth delta nu. And notice that as the coherence length and therefore the coherence time gets smaller, the bandwidth of the spectra gets larger. This is a very important relationship which was established in the unit, that the coherence time and the bandwidth are inversely related to each other. Now, that may sound like the end of a story. It is, in fact, the beginning of something rather interesting, because notice that this relationship between bandwidth and coherence time is the sort of relationship that you have between the 2 halves of a Fourier mate. It suggests, you see, that given an interferogram, we can, by means of a Fourier transform, end up with the spectrum. And in fact, we can see that this is so in the following easy special case. If you look at this one here, we have cosinusoidal fringes oscillating around this dotted line. A cosinusoid, the Fourier transform of it, well, that's just a single frequency. There it is. And in fact, it's true in the general case. Given an interferogram, we can always, by means of a Fourier transform, establish all the details of the spectrum. And that's the basis of a very important technique called Fourier transform spectrometry. Well, now let's have a look to see how this technique is put to use to solve a practical problem.
We're all concerned with what comes out of the back of a car. Not only do we have to breathe these fumes in, but they mess up the environment. Well, just what gases are present and in what composition? This is clearly the sort of question that scientists would like to know the answer to. I've come along to an industrial research laboratory. In fact, it's the Warren Spring Lab at Stevenage. They're very much concerned in this laboratory with problems of air pollution, with the environment. And one of the projects that they're working on is the analysis of car exhaust fumes. Well, how do they analyze these fumes? You might think that they would use chemical methods. In fact, they don't. They use Fourier transform spectrometry. The idea behind this method of analysis is rather simple. What they do is they take a light source and shine it through the cell. Now, by measuring how much of the light is absorbed in the cell, they can work out what gases are present and in what proportion. In fact, if we just use white light, nothing much is absorbed. But what happens if we use red? Well, in this particular case, not much is absorbed either. In fact, to get a substantial absorption, we've got to go way beyond the red into the infrared region. This is the piece of equipment that they use for the job. Basically, it's a Michelson interferometer. I'll just load our sample cell, and we'll have a look at the geography of the equipment. In this region here, we have our familiar Michelson setup. The beam splitter, the fixed mirror, and down here, the moving mirror, which is driven back and forth by means of a rubber belt. There's also a laser and a couple of extra mirrors in this setup, but that's only there to enable the system to be calibrated. The source down here produces radiation, which is collimated into a parallel beam by means of this lens here. The lens is made of germanium and is quite opaque to visible light, and if I put in this piece of ground glass, we see absolutely nothing on it. After the collimated radiation passes in the usual ways through the system, it comes down here, passes through our sample cell, and so to a radiation detector. Why, you may say, do we place the sample cell here next to the detector? Why don't we place it, say, immediately beyond the source? Well, you'll know from the unit that you can place a filter in a Michelson either in front of the detector or in front of the source. And we can think of our sample cell as a sort of filter. After all, it filters out certain wavelengths. So it doesn't really matter whether we place it there or there. In this particular case, it's easier to place it here because it keeps it away from the heat of the source. Well, now let's get back to our solid-state detector down here. The radiation passes through a small pinhole onto a solid-state radiation detector and is then converted into an electrical signal which comes out down this cable. The next thing that happens to the signal is that it passes through some electronics, in fact, through an amplifier and onto an oscilloscope. The oscilloscope traces out the results for us from the detector. Along here, we plot the separation, the path separation. That's the distance between the two mirrors. And up here, we plot the output from our detector. Let's just have a look at what we've got. Along the horizontal axis, we're plotting out the separation between the two mirrors, and along the vertical axis, the reading on our detector. In fact, the whole trace would be symmetrical about the zero path separation, which is located in this region here, but we're only displaying half the trace for clarity. The rest of it would be off to the left. Well, as we might expect, there's a good, strong signal at zero path separation, zero path difference, and quite a bit of information going way on out here. But we must be rather careful. What we're seeing on the oscilloscope here is not the spectrum of the radiation that's striking the detector. In fact, it's merely an interferogram. Well, we know that to get from an interferogram to a spectrum, we've got to take a Fourier transform. And that's where this miniature computer comes in. All the while that I've been talking, it's been storing information from the Michelson. And we'll now ask it to take the Fourier transform of the interferogram for us. And here we have the spectrum. Along the horizontal axis here, we're plotting wavelengths. Along the vertical axis, we're plotting intensity. That's the intensity of the radiation reaching our detector. Well, now, what does this tell us about the exhaust gases from the car? This trough here is actually due to absorption in our cell by carbon dioxide. It's at a wavelength around about 4.3 microns. This rather shallower little dimple here is due to carbon monoxide. It's at around 4.7 microns. And this generally depressed area over here is due to water vapor in the cell, somewhere in the region 6 to 8 microns. But how do we know that all those dips and valleys and things are actually due to the car exhaust gases? They might, after all, be due to absorption in the end windows. Or they might be due to absorption in the gas that surrounds the cell. Well, what they do is they do a control experiment. They remove the exhaust gas from here and repeat the entire procedure. Here's a typical set of results that they've obtained in this laboratory. The black curve, the upper curve, was obtained without any sample present. The lower red curve had the sample present. Quite clearly, there are differences between the two curves. But it's a little bit hard to be quite certain what these differences are. Things are made a lot clearer if we take ratios. If at any given wavelength, such as say, this wavelength here. We measure this height here and divide that by this height. And then we plot that ratio against the wavelength. Then we do the same operation at all wavelengths. Here's such a ratio in the case of a car whose engine was cold. There's a hefty absorption of carbon monoxide, so there's quite a lot of carbon monoxide obviously present. But when the car is warm, after the engine's been running for some time and the choke's been put in, we see that the absorption has gone down. The amount of carbon monoxide present has decreased.
So you can see that by automating the output, we can examine the exhaust spectra and see a way ahead to solving the problem, to reducing the amount of pollution caused by car exhausts. We can solve a practical problem. Now, at the heart of the method, there's the interference between two beams of radiation. And you might well be wondering why we don't use a simpler system in order to do this, namely the double slit. After all, in the unit, we use the double slit to introduce many of these ideas, which are essentially about temporal coherence. Well, the problem is one of path length. You see, regardless of how far we move up the screen, we can never get a path difference for the two beams of greater than d, the separation between the slits. Now, this means that we can't handle spectra that are very narrow. We can only handle broad spectra. You might think that we can overcome this difficulty by increasing d. But in fact, this gives rise, as you will know from the unit, to very small, very narrow interference fringes, which are very difficult to observe. We can't get over this particular problem. Now, by contrast, the Michelson doesn't have this particular problem. We can wind that mirror back as far as we like to establish the interferogram that we're interested in. And once we've got the interferogram, we can be sure that we can work back from it and establish for any source the details of its spectrum.